Hi everyone, and welcome to a new video about control system topics, and we continue with the subject of stability, and in particular with Routh-Hurwitz stability criterion. And this is our example number 8 already. And in this example I would like to discuss the stability of a PID controller. So we have a PID control system and we would like to check the stability for several parameters of the PID controller. So what we do, again, we will start with the calculations, analysis, and then we will check our analysis using the simulation in MATLAB. So let's look at our example. Now we have the following diagram. Closed-loop system is given. We have the PI controller in cascade with our plant. So PI controller is given as DS and the plant is given as GS. So we have now the expressions here for the plant, which is a second order system with two real poles and are both stable. So we have already an open loop stable system. The PI controller here is given by this expression, ds is equal to k1 plus k2 over s. So we have the pure integration part here and a pure gain part there, and that will be added together. So we have two parameters, two unknowns. That's actually the question also in place. Determine the values of k1 and k2 of the PID controller such that the closed loop system is stable. So we start again step by step analyzing this problem. So what we have, first step is determine the characteristic equation of the closed loop system. And the characteristic equation is given by 1 plus the loop gain, which is 1 plus ls is equal to 0. And the loop gain, where loop gain is now in this case, you make the first full circle and you determine actually your loop transfer function, which is ds times gs times 1, which is just unity gain feedback, and then you have your transfer function. Let's first write the expression for the PI controller a little bit different. That will be helpful in the later analysis. So I have now just multiplied the k1 first term numerator and denominator by s, so I make a fraction actually for the first term. This will allow me to make this in one, put this in one fraction. So I will have the following expression. Now I will use this one in the loop gain transfer function, and also in this expression for the characteristic equation. So I have 1 plus, this is the integral part, this is the loop, open loop transfer function. I have now the expression. Now if I now simplify this in step-by-step form, I have now this together, and now multiply right hand side and the left hand side with s times s plus 4 times s plus 8, and then I have this expression. Now what I want, of course, always for Routh-Hurwitz stability criterion, I would like to have this in a polynomial expression, which is not at the moment. So if I now work out the parentheses, and a couple of steps later, I have this expression. And this is actually what I wanted, and this is the characteristic equation. So we have our characteristic equation, and we can now see the coefficients, and we will use this in our next steps. So the next step is generate your route table. So that's actually our next step. This is already given as the third order table. So we have the general third order table, and we will now see on the right side the third order polynomial in a general form, and this is our characteristic equation. We have determined that earlier. So this is our characteristic equation. We can now see what A3 is, A2, A1, and A0. So we can just see a pattern there. So A3 is 1, A2 is 12, so A1 is 32 times between parentheses 1 plus k1, and a0 is 32 times k2. This is already given here. So I will substitute that, of course, in here, but I need, of course, also b1 and c1 in order to determine the stability for this system, because I need to check the first column. If there are sign changes or the zeros, that's actually the situation. So I need b1 and also c1. So let's first do that. So I will again start with the row of s to the power 1, which is now shown here for the calculation. So b1, again, the familiar formula we have seen in the previous examples. I just substitute the value of a3, a1, a3, a2, a1, and a0, what we have also seen here, and divide by the a2. Now, if I do the math here, I will get this. I will substitute that shortly in the table. b2 is in a similar form, but this is in the third order system always 0, and b3 is always 0. Okay, now we have now the b's. Now let's look at this part of the table, which is the last row for s to the power 0. That means actually the C1 first. So again, in a similar form as we did in the previous examples, again the formula, you substitute the values, you will get here 32K2. And this is also almost the case. What you have actually here for A0 will be actually here at C1. Now, if I do the math for the others, C2 and C3, it will be always 0, but for completeness, I have put it in here. So we have now determined the necessary elements in here. I can now substitute the values in the table, and I have the following expression. Now, these are from the characteristic equation, and these two I have just determined, and these are always 0 for the third order system. What do we next? We evaluate, of course, the stability for using this first column here. So let's do that. The next step is evaluate the values of K1 and K2 for stability. That means this column must not show any sign changes. So if I started with a positive number, and again positive, so 1 and 12, and this must be also positive, and this must be also positive. So I have two conditions, which are now, from the root table, we see that we require the following condition, no sign change in the first column. Again, if I now write it down, this is actually for this part. So 32K1 minus 8/3K2 plus 32 must be larger than 0. And not only that one, 32K2 also larger than 0. So both of them we need both of them. Now, if I continue with the analysis, just simplifying the expressions here, I just place this and that part over the second and third part of the right side of this expression. I get this, and this is of course just divided by 32. You will have already the first condition that K2 must be larger than 0. Okay, now if I just simplify this even further by dividing the left and right hand side of this equation by 32, I get the following expression. In fact, it is just a linear function, and we will see that later on, because if you consider this as a y and this an x, so you will see this is 1/12 times x minus 1 is just actually your y. So we have now two conditions. K1 must be larger than this expression, 1/12 times K2 minus 1, and K2 must be always larger than 0. If I, for example, make K2 4, then I have 1/12 times 4 will be 1/3 minus 1, and that will be minus 2/3. So this is actually the expression which you need to meet first, and that will of course result in an expression for K1. So there is an interaction between those two conditions, so we need to consider that in more detail, and let's check that. Now again, I have the table and also the required conditions. For this system, because we have now two parameters, we need to actually check for an area of stability, so allowed area for stability. Now if I now, again, since we have two parameters, we need to check that in terms of area, not in terms of line. So from this allowed area, we can then determine the values of K1 and K2 in a more precise way. Now, setting the K2, as we said earlier, as on the x-axis, we can also do it for the K1, but I think K2 is easier, and make the K1 on the y-axis. Then we can draw the allowed area. We will do that shortly. Now, if I now set just K2 is x and K1 is y, just as a mathematical expression, now the following requirements we still need. K2 must be larger than 0. This requires that the allowed region is at the right side of your y-axis. And if this condition must be met, that requires actually the allowed region is above the line y is equal to 1/12 times x minus 1. So there's actually two expressions, and we will see shortly if I draw the expression what happens. And the intersection is actually the region where we have the situation for stable system. So if I now look at the right side, you can see I have on the x-axis the K2 and on the y-axis K1, as we've discussed here also. And this is actually the line which you see here. You can check that by using 2 points. For example, if you make x equal to 0, which is K2 of course, then you will have 0 minus 1, which is of course minus 1. So it starts at minus 1. And if you substitute here 12, you will get 1 minus 1 will be 0. So you can actually check 2 points, and that will be sufficient for this linear expression. Now, for the expression of k2 must be larger than 0, that means actually everything on the right side of this vertical line, which is actually shown here, is allowed, and left side is for sure not allowed, and everything above this line is allowed, so everything above this line. And if I now find the overlap between these for these two conditions, I get actually this allowed region. Of course, this extends also above and to the right side, but you can already see that this is the allowed area for stability. It is not just one number. You can see that there is a collection of values. So for example, if I take k2 is say 10 around here, then I can of course take for k1 a value between this value and that value. If I go under that value, I have a problem and it will be unstable. That's actually the condition for this system. Now, let's go in more detail and let's look at some cases that will be helpful. And I will again present here the table, and I will now choose several values for k1 and k2 in order to check what will happen for our system. So let's first start with case A, which is I make k1 0 and I make k2 12. This in principle, this is just a pure integral action. So if I now substitute the values for k1 and k2 in here, I have the following table. So this is actually just substitute what we have here, just place here as 0 and make this 12. So you will just multiply everything and you do the math. What you see is, if I now look at the first column, I see a 0 in here. That already suggests that there is a marginally stable system. So we need to check, since we have also here a 0, we need to check the stability condition by looking actually at the row above, and that is what we call auxiliary polynomial PS. So let's look at that. PS is now, because this is the s squared term, that will be 12s squared plus 384. That's all. And this is actually expression. And if I now check the solution of this expression, which is just make that equal to 0, and just substitute the values, you will now have s squared is s squared plus 32 is 0. And if I now do the math here, I will get two poles which are pure imaginary, and of course in pair. So I have omega n, which is the natural frequency for this case, and that will be square root of 32. And if I now approximate that, it will be 5.66 radians per second. Now this is the marginally stable, and this is our oscillation frequency also. So this is the oscillation frequency, and now this is an approximate form. I can also calculate the oscillation period, which is the T oscillation is 2 pi divided by the omega n. And if I substitute the values, I get approximately 1.11 seconds. Now, we can check this using the simulator and, for example, MATLAB, and I can plot the step response, and we will see that we need here, in this case, a sustained oscillation at the output. So we need the sinusoidal waveform. Let's check that, and this is the plot I have now prepared here. You can see that the step response, unit step response, shows indeed a nice sine wave at the output. What you also see is, I've put some labels here, that the peak, the distance between two peaks, the time, is 9.52 minus 8.41. So the oscillation is, if you calculate this, you will get 1.11 seconds, which is actually what we have calculated. So it's exactly correct. Now, I can also check this situation that there is a marginally stable condition using the root locus plot, which is actually shown here. And we see all the poles of the system. And these are actually the open loop system poles. We have the -8 here and -4. And these poles given in pink color, which are actually the closed loop poles. And as you can see here, there is a pole here, pole pair actually. And this causes actually that the system is oscillating in this form. And there's another pole, is the third pole, which is at -12 approximately, and that is of course not causing any instability, but this is at the marginal stable position. We can also see at the natural frequency, which is omega n, also 5.66 radians per second, also from the simulation. So this confirms actually also that there is a marginal stable position in this case. Okay, let's look at another case, case B. Again, we have a table. Next, case B. I make K1 is -1 and I make K2 0. This is again an edge of instability, so let's check that also. Again, I substitute all the values. I have K2, which is 0, that will be 0, this will be 0. Since this is -1, this is also 0, so I have a lot of zeros. You can see this. And this is -1, and this is 0, so I will have -32, -0, and +32, that will be also 0. So 0 all over the place. I have just 1 and 12 here. And this is now producing actually more zeros here, and I have to now check this in a different form. That is actually the situation what we have discussed in the special cases of the Routh-Hurwitz criterion. I have now a row of entire zeros. So this is all zeros. So entire row. So we have now also the situation that we need to check again above that row. So we need to check the auxiliary polynomial PS again. Let's set up the equation as we did also in the previous case. What we have is then for the expression for PS is 12s squared plus 0 actually. So I just put it in purposely here to make this more clear. If I now again want to calculate the associated pole for this one, I just equate it to 0. If I now calculate this, you will have s squared is equal to 0. S squared equal to 0 means actually there are two poles, because the condition here is that s is equal to 0 and s is again equal to 0. So you have double pole at s is equal to 0. If you have a double pole at the origin at s is equal to 0, you have actually a double integrated integrator. And if you now do a step response, you apply a step input at a pure integrator, which is now double integrator, you will have an unstable system that will actually blow up in a linear fashion, but it will never come to a constant value. It is also seen in the unit step response we have prepared here from the simulation, and it is now the case B, as you can see here. If I now apply for this system using these two values for the K1 and K2, I see that the gain or the output actually keeps increasing. So it started at 0, and it's inverted because there is a sign of -1 here. That's actually the case, but you can see if you ignore this, that this is going down, it is going, it will increase without any bound. So this is for sure unstable. You can also check that using the Routh-Hurwitz plot. It's not really accurate to see here, but we have a double pole in this region, and another pole is here. So if I had another pole, I should of course see another pink dot, but there is no other pink dot. So this one is -12 approximately, and this is actually the two poles at 0. So this condition is unstable for case B. Okay, let's look at the case C. Again, the table. I make now K1 is 1 and K2 I make that equal to 0. That means this will go, this will go, this will be, of course, in this case 64, because this is gone and I have 32 plus 32, and this will be also 64. Now let's substitute the values. I have now the table here in this, for this case, case C. Now I see 1 0 here, so I suggest again it can be marginally stable maybe. But is it marginally stable? That's the question. Let's check that. Again, we check the auxiliary polynomial above this row, and this is actually what we have. What we can say is s to the power 1, and we will have 64s plus 0. So PS will be 64s plus 0. If I now, of course, equate it at 0 and calculate what the value of s must be, that is just 0. So we have a pole actually at the origin, but there's just one pole, so single pole. And that doesn't cause any unstable condition. So for step input, I will have still a stable output. Now this is now the unit step response I have prepared, and this is now case C. What you can see from this situation is I have now a step response. It will show the situation as shown here. What you also see here is, in this case, that this situation is actually a proportional control action. You might ask why? Because I have now made the K2 0 and I have only left with K1, which is actually the controller gain. And you can also see, so the steady state error is not 0, that means actually we have a proportional controller action. So that's actually what the situation is here. So there is a final value which is not 1 but 0.5, so you will have a steady state error. Okay, let's move to the case D. Again, a table here, and I make now K1 is 0 and then K2 11. It is purposely 11, lower than 12, because the 12 was the edge for situation when you have the K1 is 0. And this is a stable pure integral control, and we will see what this system will do. If I now substitute the values for K1 and K2 in here, I will generate this table. You will see in the first column no sign changes. So we can already conclude no sign changes. That means stable system. Now let's look at the unit step response. What we have is a lot of overshoot, but still stable, but it is a lot of ringing. And the final value is 1. That means indeed we have a pure integral control, but we have a lot of oscillation. So we can of course improve this, but the thing is, it is stable. It has a 0 steady state error if there is a requirement like that, of course. And we have actually designed the system according to stability only. Now, if I want to make this, of course, a little bit better, I can add the proportional controller part also, and I will do that in case E. And you can see here that indeed the steady state error is 0, and it is pure integral control action. So let's look at the final case, case E, which is now I make the K1 is 2 and I make the K2 6, and it is now stable PI control. Now if I substitute values in here for these two conditions, I have the following table. Again, first column will show us that it is a stable system because we have no sign change. Again, stable system. I can already say that. If I look at the step response, I can see the following. The overshoot is decreased a lot, so it was just at case D was approximately 80%, and now it's approximately 7%, so it is a huge improvement, and also it is much faster. And I see again that the final value is 1, because this action also includes a integral control. So we have no steady state error, so steady state error is 0, and I have now PI control action. And this is actually one of the best options for the 5 cases we have discussed now. We have 0 steady state error, the overshoot is okay, and the system is stable. If you of course want to design this for a specific overshoot and for a specific settling time, there's another discussion, and we can use then the frequency response method or the locus method that will be also discussed in another video. But this particular example was considering actual stability, and we'll have checked also the situation when we have different values for K1 and K2 in our PI controlled system. Okay, that was actually for this example, having calculated and simulated the results, and we have converted our analysis. Again, thank you very much for your attention, and I'll see you next time in another video. And if you have questions, comments or suggestions, please let me know. Have a nice day and take care.